Everyone, and welcome back to the 2023 CINR webinar. We're going to resume this afternoon with topic area 2, fuel cycle technologies. And the very first presentation will be by Stephen Kung for FC1 aqueous separations chemistry. Stephen, when you're ready, go ahead.
All right, thank you. Okay, good afternoon. My name is Stephen Kung. I'm going to kick off this afternoon section, starting with topical area 2, fuel cycle technologies. So 2 nuclear energy offices involved in this specific topical area. The one is NE43, Material and Chemical Technology Group, to cover FC1, aqueous separation, and then I will be the federal POC. And then we have FC2 on molten salt separation and solution chemistry. My colleague Jim Willett will cover that topic. We also have NE81 spent fuel and waste disposition program to cover FC3, focus on waste disposal, and FC4 on storage and transportation. My colleague John Orchard will cover those 2 topics. And then we also have FC5, which covers all other fuel cycle related topics we are not covered under the previous 4. So next slide, please. Yeah, I want to give an overview of FC, the fuel cycle area, fuel cycle technology. So as you know, we at NE, we develop sustainable fuel cycle technology and options to improve resource utilization, reduce waste generation, and enhance safety and limited proliferation. So in this regard, we have a fuel recycling and separation chemistry activity. Another office is covering the repository for the responsible for the repository of managing and disposal of commercial high-level waste. So in this case, we will have a used nuclear fuel disposition R&D program to cover that topic. So for the first, for the fuel cycle area, our goal is to focus on developing advanced fuel cycling technology and address fundamental material separation and recovery challenges. For the disposition R&D program, we conduct scientific research and technology development to enable long-term storage, transportation, and disposal of nuclear fuels and waste. So an additional research opportunity involves development of processes and the tools and to evaluate sustainable fuel cycle systems and use fuel management options and can communicate effectively to stakeholders. So basically, there's other areas we are not covered. So next slide, please. So to begin with FC-1, that's my area. So our current focus is to develop a simplified single cycle process. So we seek your help to provide innovative approach that can improve our fundamental understanding of aqueous separation to enable simplified cycles. As you may know that current baseline material for our aqueous separation is Purex and Urex. And Purex, Urex are considered mature technologies. They are very good in terms of separate plutonium and uranium. But the drawback here is a high capital cost and operation cost. So we seek your help to simplify this. So in this case, we also want to get away from the conventional TBP, tetrabutyl phosphate process. In this case, we want to eliminate the phosphate issue there. So we want to develop an alternative process here. We listed a couple examples here. The first one is innovate leak design and synthesis. And then we want to understand molecular level interaction of interface. And also we want to use external force or field to enhance the aqueous separation. And the last one, we used examples, developed real-time quantification chemical species technologies. So in our program, we use a kind of a workshop to help us to identify our research priority and directions. In FY21, we conduct advanced fuel cycle workshop that's listed in the very bottom of this slide. So we have a report published earlier 22 this year. So you can download that report. So innovate separation R&D need for advanced fuel cycle workshop report from the URL I listed below. So this will help you to understand better our program directions. Okay, next slide, please. All right, we will ask to give you some kind of current work relevant to FC1s. So I just want to give you a current R&D activities. Again, we focus on simplified single cycles. Most of them are conducted at national laboratories. So the first item is we establish simplified single cycle baseline using model amides. So in this case, we are using the DEHIBA, DEHIBA, versus DEHBA, DEHBA. So basically, this is a kind of improved, or not improved. This is the basis for group separation. So AKA also called GANX process. So we move away from a conventional Purex and then go to the GANX process. Our European colleague has conducted quite a bit of this research, but in the US, we have not do much in this area, so we're trying to catch up. So we try to use GANX, our simple baseline here, using the DEHIBA as our baseline mono amide examples. And then we also use AI/ML, machine learning aided ligand design synthesis to tailor actinide separations. So in this case, we try to develop simplified methods for managing problematic transition elements. In this case, it's more like ruthenium, technetium, zirconium. And also, we are interested in Neptunian separation as well, because we also consider the partitioning of Neptunian is considered a problematic element. So the second item is evaluate promising novel organic aqueous-soluble complexant. In this case, again, we want to move away from phosphate-based TBP. So we want to use CHORN, CHORN elements there. And the last one, design and optimize innovative recycle system. So, and flow sheets there. And next item is explore autonomous testing system and machine learning to accelerate data acquisition. So in this case, we have Los Alamos and Oak Ridge doing this similar work area. So I think the specific PI is for Pingyang and Shandai, this area. And I want to mention one thing is my colleague Daniel Nichols also has a RDO-5, I believe, called implementation of AI/ML area. So if you are interested in developing AI/ML visibly as a tool, so then you may also consider Daniel's topical area. That's RDO-5. And the next item I have here is direct dissolution of oxidized fuel into organic phase. So we're trying to eliminate the acid dissolution. In this case, we can avoid the strong acid and nitric acid dissolution that will significantly reduce the back end the waste issue here. And then the second to last is the development option for recycling advanced reactor fuel type. In this case, a lot of advanced reactor fuel using HALEU materials, they are 20% U-235 to start with. But after they deployed for the advanced reactor, they may still have plenty of U-235 left in the spent fuel. So our goal to simplify this is trying to extract those useful U-235 from the spent fuel there. So that's part of the GANX. The first step that they call the GANX 1, just just extract the uranium portion, and then the GANX 2 trying to separate the two together. So we haven't reached the second stage yet, but we are really interested to develop alternative methods. We are not happy just with GANX itself because we believe GANX can be improved, further improved. In this case, we try to simplify that. So, and the last one is to understand the innovative managing and control of irradiation damage. So in this case, Greg Horns from Idaho is our lead researcher in this area. So if you are working in this area, you probably know him very well. Okay, next slide, please. All right, so we also are asked to state what area we are not interested. For the first item I list here is recycle of max fuel from light water reactor. So as you may know, our European colleagues focus a lot of their energy into this multiple recycle and the reprocessing of max fuel. We are not very interested in this area. Please do not submit a topical for this area because we don't even have the first recycle use of max. So why bother to recycle multiple recycle of max? And so this is very different, and we don't have a max certification plan. So our current fleet are not using max at all. So don't consider that. And the second one is we're trying to avoid the evolution of TPP based technologies. In this case, we are not interested in incremental improvement of Purex or Urex technology. Again, we want to get rid of TPP, trying to use substitute or even just totally eliminate that. And the third one is minor actinide separations. So we spend a lot of energy in the past 10 years to do a lot of minor actinide separation for different purposes. But end of the day, we developed a good technology, but it's really increased the complexity of the separation process. So that goes against our current idea, try to simplify. The end of the day, we want to simplify this to reduce technology cost. So that's economics is the driver for our current thinking here. So the next one is we want to avoid the hybrid aqueous and the non-aqueous methods. So basically, some people propose using aqueous and the salt, a combined process to do this separation. Again, this is very complicated. One for aqueous already complex enough. So if we added pyroprocessing system, it's really a further complicated system. So unless you can justify why this is enhanced simplicity, please don't submit a research area in this topic. And then we have give you some kind of example for proposal topic we can submit to FC5, other fuel cycle technology. In this case, that's not covered under aqueous or not covered by the salt process. It's advanced oxidation. It's a gas phase separation or vapor phase extraction. So in that area, you can go to the FC-5 for proposal. That's all my presentation. Thank you. Jim, you want to take over the FC2?
Sure. I guess we'll deal with questions at the end of this section. Okay, so this topic FC2 focuses on molten salts in terms of separations using molten salts as the process fluid as well as just solution chemistry of molten salts. They really have unique composition dependent chemical, thermodynamic, thermophysical, and neutronic properties that really make them well suited for the front back ends of nuclear fuel cycle, as well as molten salt reactor fuels, as well as thermal storage. They have large liquidus ranges, heat capacities are good. There's no degradation of these high temperature molten salts. I'm talking about typically metal halides. Will also include metal nitrates as well. So these unique properties are really determined by what's going on at the atomic level in the molten salt solution. There's different complex anions that are forming dimers, oligomers, all kinds of interesting phenomena that go on at the atomic level that really affect the chemistry of the solution as well as the properties. So with this topic, we're seeking proposals on a combination of innovative modeling and experimental approaches to more accurately predict and characterize the speciation and structure of molten salts. And we're doing this. This is really driven by, we want to improve our fundamental understanding of the solution chemistry of molten salts. Things like activity coefficients, formal potentials, vary very much with the change in the structure of the salt. And also the atomic level affects the solution properties, things like viscosity, density, surface tension, solubility of oxides, and things like that. Next slide. So the Fuel Cycle Initiative and NE has been supporting ongoing and fundamental applied research through lots of places, through NEUPs, SBIRs, industry FOAs, as well as the direct supported programs at the national labs. And rather than give a couple cherry-picked examples, really you can, because this general topic area has been a NEUP area of research for several years now, and it's easier to go back and look through what the fund projects that have been funded, and I give a link there, and even just if you click on a year under final project reports, it'll give reports that are available under OSTI. If you click on a year under the list of NEUP funded projects, and then select fuel cycle research and development, it'll give a list of projects that began that year and search for the word molten salt, and you'll get an idea of the kind of work that has been funded. You might find that what you thought was an interesting idea is something that has been funded, or you might find that it's not been funded, or something you see as a follow-on for what has been funded. There's additional information available from a recent workshop. The title and the link is given there as well. This was focused both on molten salts and back end separations and front end, as well as molten salt fuels. So typically funded projects have combined modeling with experimental measurements that really provide insights on the speciation atomic structure of one or more molten salt solutions. So what could be done is looking at solutions that haven't been looked at before, different approaches, different experimental techniques. Encourage you to become, if you're not familiar with the work that's been done in this area, to spend some time becoming more familiar with what's been done, and that does two things. It keeps you from proposing something that would be considered duplicative, as well as when I do that, that kind of literature dive usually ends up being more stimulating for new ideas that you didn't have before you did the dive. Next slide. As other people have said, these applications should focus on research that supports the DONE mission. In the past, it's been the mission and ongoing programs, but this year the scope has been broadened, but it still is within the boundaries of the DOE NE mission. Molten salt proposals with the following focuses that would be considered not really relevant to this topic. One would be with proposals involving what a lot of times called room temperature ionic liquids that are based on organic ions. Those don't have the temperature range that is of interest to NE, and they don't stand up to radiation as well, and typically they don't have as wide a potential window either that you could actually deposit metal out of it. Concentrated solar power applications, although there is some overlap because these are heat transfer fluids or heat retention fluids, but those really, this is not the call really for work on concentrated solar power. Molten salt batteries, again, not really directly related to this. And lastly, this is for dealing with more molten salts, not separations based on fluoride or chloride volatility or halide volatility. This is on the condensed solution chemistry. Measurements, I guess, of vapor pressure or being able to predict vapor pressure might be useful. That's just a general application for the molten salt, but not really as a core separation method. I believe that's my last slide.
Okay, good morning.
Hey, John.
John. Yep, I'm here. Can you hear me?
Yes, John, we can hear you. Thank you. Go ahead.
Okay. This is John Orchard. I'm with DOE NE 81, which is Spent Fuel and Waste Science and Technology Group. I'll give you a quick overview of who we are and then list the activities we're doing and some not to propose topics. As our country continues to develop nuclear energy as a solution for decarbonization, increasing access to energy, and tackling climate change, we need to make progress on the back end of the fuel cycle. The U.S. Department of Energy Office of Spent Fuel and Waste Disposition is responsible for managing the nation's spent nuclear fuel and high-level radioactive waste, including finding sites to store and dispose of the spent nuclear fuel. To focus on this challenge, the Office of Spent Fuel and Waste Disposition has established two offices. The Office of Integrated Waste Management, which is the applied side that focuses on the design and siting of consolidated interim storage and preparing for transportation to the interim storage. And the Office of Spent Fuel and Waste Science and Technology, which focuses on the R&D side, which is my side. The mission of the Office of Spent Fuel and Waste Science and Technology is to provide a sound technical basis for the safety and security of long-term storage, transportation, and disposal of spent nuclear fuel and high-level radioactive waste from commercial nuclear power plants. Next slide, please. The first mission, the disposal research mission, is to provide a sound technical basis for assurance that the U.S. has multiple viable disposal options for mine deep geologic repository available when national policy is ready. To identify, research generic sources of uncertainty that challenge the viability of the disposal concept. Also to increase confidence in the robustness of generic disposal concepts to reduce the impact of site-specific complexity. And develop the science and engineering tools required to address the above needs. Our mission is to look at the generic disposal concepts, and the third item there is to reduce the impact of when we look at site-specific disposal sites to reduce the complexity in applying them. Next slide, please. There are some representative activities that we have or plan to perform in disposition and disposal research. The first is one of the first host rock, or one of the host rocks that we look at is argillite. And there we're looking at the effect on repository performance of the coupled THMC processes, that's thermal, hydro, mechanical, chemical processes. Integration of process models into the GDSA framework, the geologic disposal safety analysis. Modeling the THMC processes within the EBS, which is the engineered barrier system. The second host rock is crystalline, and there we're looking for flow and transport and fractures. We're looking at modeling, coupling the THM, thermal hydromechanical processes affecting fracture transmissivity, and performance of candidate buffer materials. Next slide. We're also looking at salt disposal, and there we're looking for effects on heat generating waste on the performance of the salt. We're looking at the evolution of engineered barriers in salt. We perform the brine activity test in salt, borehole completion and setup. We performed that activity, and we're continuing to look at model development. A fourth area is we're looking at the engineered barrier system, and there we're doing experiments on bentonite, cement, and waste package materials at higher temperatures. We're analyzing the effects of thermal, mechanical, and chemical processes on the performance of the engineered barrier system designs for each of the 3 host rock types mentioned above. And we're modeling bentonite clay, dehydration, swelling, and creep, the thermal hydrogeologic behavior of the barriers, of the barriers. Next slide, please. Our geologic disposal safety assessment, we're looking at the capability expansion of the framework, such as fracture transport, high T systems, uncertainty, and sensitivity analysis. We're developing a surrogate model with approaches and advanced solvers, developing advanced solvers. The Decovalix 2023 reference cases for the International Performance Assessment Model comparisons. And we're looking at cladding degradation model for post-closure criticality configuration and short-term performance. We also have a project to look at direct disposal of the dual-purpose canisters, which are already in existence. And there we're looking at filler experiments and demonstration performance criteria. We're looking at hydrothermal testing of the zircaloy cladding, and we're looking at the criticality consequence performance modeling. Next slide, please. Those are areas that we have been focusing on, and applicants should focus on research that supports these areas in the spent fuel waste science and technology disposal research mission. The following areas we would not consider relevant to the mission. These include technologies not primarily related to deep mine geologic repository issues, technologies solely related to site-specific issues, as I say, we're looking at generic sites, technologies solely related to Yucca Mountain repository, which we've researched thoroughly, technologies solely related to deep borehole disposal, which is not a current pathway, technologies solely related to tough host rock, which is the host rock at Yucca Mountain, and technologies solely related to international disposal issues. If they relate to our issues, happen to include international disposal issues, that's acceptable. The applications on technologies that cross-cut with any of these areas could be considered responsive if they clearly demonstrate relevance to the mission. As I said, solely related, if they incidentally include information on these areas that I said are not relevant, that's acceptable, but they must focus on the core mission. Next slide, please. Our second mission is storage and transportation. And in that mission, we're developing the technical bases to demonstrate fuel integrity for extended storage periods, to support fuel retrievability and transportation after extended storage. And we also are looking at transportation of high burnup fuel, which is becoming more prevalent in the industry. Next slide, please. current activities that we're performing is fuel integrity testing and analysis. We're doing destructive testing and inspection of high burn-up fuel sibling pins. We have a high burn-up fuel demonstration project where we've loaded actual discharge fuel pins or fuel bundles into a canister, and we've taken sibling pins and we're doing testing and inspection of these sibling pins to look at the initial state of the fuel that was loaded into the canister, the demonstration canister, so that in the future when we remove the pins after storage, we'll have a baseline. Second point is continue phase 1 testing and discuss the plan for phase 2 testing. And we can go into more detail on what the phase testing is. Dry storage canister stress corrosion cracking. The big issue is that we're developing quantitative and sampling methods for dust sampling of the canister deposition field demonstration, which is another field demonstration. We're collecting and analyzing frozen test data, and we're evaluating crack repair mitigation coating studies for the storage canisters to repair and mitigate, inhibit the stress corrosion cracking in the canisters. Next slide, please. The previous topic was developing technologies to prevent, inhibit, repair the potential chlorine-induced stress corrosion cracking. In the meantime, we're also analyzing the failure consequences if we do have a crack. And so we're performing aerosol source term analysis to quantify the time evolution of the sequestral fraction and aerosol transmission through idealized stress corrosion cracks. Then we're also doing external load testing and analysis on the storage canister and the storage canister internals, including the fuel bundles, the fuel rods, and the fuel. And part of this is we're planning seismic shaker table test for a full-scale canister, including the storage overpack or module. Initially, we're looking at a vertical storage overpack. In the future, we might be looking at a horizontal storage module, which we are loading the canister with surrogate and dummy fuel, and putting it in the storage overpack, the module, putting it on a shaker table, and applying representative loads from earthquakes, etc. And this includes the design and fabrication of the vertical concrete cask and the dummy assemblies, which will be on site at the University of California in San Diego. And we're doing seismic pretest modeling of the cask and soil structure interactions. Next slide. We're also looking at thermal and drying of the fuel, and we're testing perform testing updates for the dash pump drying apparatus. We've had international round robin modeling of the high burn up fuel demo, and we're performing small scale testing drying methodology. We're developing that. The canister deposition field demonstration, which I mentioned earlier, we're instrumenting sample canisters and applying heating elements for testing. And we're performing surface sampling methodology, shakedown protocol development on these sample canisters in the field demo. The idea is to recover dust that's deposed on the canister to analyze the composition of the dust and the frequency. And then on the high burn-up fuel field demonstration, which is the loaded canister demonstration I mentioned, we're going to continue modeling and interpreting the canister temperature, and we are designing and preparing the facility and procedures for investigating the contents of the fuel field demonstration canister when we open it in the future and remove the fuel bundles and fuel rods and do the inspection, the testing and the inspection of the fuel rods. And then we'll compare it to the sister rods that we have already looked at. Next slide, please. And so again, the areas that we're not interested in include technologies not primarily related to storage and transportation of domestic spent nuclear fuel and high-level radioactive waste. Technologies not primarily related to conventional light water reactors and high burn-up fuels. Technologies solely related to site-specific issues. Technologies solely related to consent-based siting issues. We have our other group in spent fuel waste disposition is the integrated waste management system, which is looking at the consent-based siting. And technology solely related to design or operation of storage or transportation equipment or facilities, which is also under the auspices of the integrated waste management division. But once again, applications that cross-cut any of these areas, as long as they're responsive to the storage and transportation mission, will be considered. Next slide, please. I think that's the end. Yes, this is FC5.
In these areas, I consider this more a catch-all for whatever we are not covered in previous topical area, for topical area. So in the following four bullets list the mission of our program, our NE program. So anything you think relate to the fuel cycle technologies regarding reprocessing, all the disposition, transportation, storage, it's not covered previously, then we can use this topical area to cover your proposal. John, anything to add?
No, I think that's right. I think you mentioned, but it says here if it's it can be cross-cutting. It doesn't have to be directly any of the topics that we mentioned above, but it has to address one of the missions that we talked about above. Yes, that's all.
Yeah, but it's in the fuel cycle technology area.
Yeah.
All right, thank you all for your presentations. And as a reminder to everybody, you have the ability to type in work scope specific questions in your control panel under the questions section. So if there's any questions, please go ahead and type those in and we will address those as they pop up. But right now we have one question for FC2. So this will be addressed to Jim. And for FC2, viscosity and density were listed as properties of interest. Are other thermophysical properties of interest, such as specific heat or thermal conductivity?
Yes, those I just gave those as examples. Yeah,
Okay, thank you,
thermophysical
Jim.
properties in general they tend to be more interest under the fuels. area like for molten salt reactors. And so if there's another area that Dave Henderson deals with, which also includes modeling, and molten salts would fall under that. So it's we had a conversation the other day that, what if things fall more under fuels that are get submitted to under FC2 or vice versa? And we said that they would get sorted out, I think is the solution. But yes, so other thermophysical properties are of interest too.
Thank you, Jim. The next question deals with trisofuels, and it sounds like the disposition of trisofuel would not fall under FC4. Would that fall under FC5?
John?
This is John. I would put under FC5, but our mission in spent fuel and waste disposition is to address current fuels, which are the light water reactor fuels, and therefore we wouldn't be addressing triso fuels. So it certainly wouldn't come under FC3 or 4. I don't know how well it would be received under FC5 because it would not apply to FC3 or 4. That's my position.
Okay, thank you, John. Is radiochemistry still being considered under FC3 or FC4? It seems like all of the examples focused on non-radioactive components of storage disposition approach.
Can you repeat the question again?
Yeah, it says for FC3, FC4, all of the examples seemed focused more on the non-radioactive components of storage and disposition. So is radiochemistry still being considered under FC3 or FC4?
John,
This is John.
your call.
Yeah. I'm trying to think of what you mean. The radiochemistry is would be most applicable under FC3, the disposal research, where we're looking at the groundwater fate and transport of the radionuclides that would escape from the waste package. So we're looking at that in the geosphere, in the host rocks. So yes, that's an issue there. Radiochemistry in FC4, we're not the fuel rods that we're looking at for are radioactive, but we're not really looking at the radiochemistry of the fuel rods because they're basically static at that point at time. We do look at the off gases, but basically I don't think radiochemistry would have an application in FC4, and it would have it might be applicable in FC3 depending on what the scope is. And again, you can always put it in FC5 if you see how it would cross-cut with FC4 in particular. I mean FC3 in particular. That would be my answer.
Thanks again, John. I do want to go back to the question that was related to the disposition of TRISO fuels, just to mention that there is a specific TRISO fuels work scope topic that will be presented later this afternoon. So that will be in topic area 3, starting at 3:30 p.m. Eastern time. The next couple of questions are for FC2. The first one of those is, are thermodynamic measurements of molten salts using calorimetric methods of interest?
Yes, provided that they are, I guess, not repeats of things that have been well characterized already. And again, it's you know, that's sort of a, you know, we want to understand the properties of the salts as a function of composition, and at the atomic level. So that's, you know, if a modeling component, I'd say, is part of that for explaining these things. But it's always good to have good data to benchmark your models against as well. But yes, you know, DSC type measurements, heat capacity, all that is useful. I encourage you to look at the data that's out there and look for gaps, or data that seems to have a lot of disagreement as far as the values, rather than just, you know, repeating things are already well established. But there are plenty of gaps out there.
Thanks, Jim. Another question for FC2. Among the molten salt systems, both chloride and fluoride of interest?
Yeah, I would say yes.
Okay, and then there's a couple follow-up questions to that. Are other systems of interest as well?
There's, I mean, my experience has been with chlorides and fluorides. I know that, I mean, there's other high temperature molten salt systems as well. You're looking at, I would say, different anions other than the halides, or
Yeah, Jim?
or what? Stephen? Yeah.
Yeah. So if you can justify this is for nuclear energy application, we welcome that.
Yeah,
but mostly we use fluoride and chloride system mostly in our case. So some salt system applicable to EERE solar system, we are not interested in.
Right.
Okay, great. And then another follow-up question to that is, of chloride and fluoride systems, which one is more important?
This is a loaded question.
Depends on who you ask.
we depends on your application. Yeah.
Yeah, I would say they both have, you know, very multiple areas of interest to the Office of Nuclear Energy.
On a similar note to that, are there any particular salt compositions that DOE is interested in?
Again,
we are not really tell you what is our interest or not our interest. It's up upon the applicant to make that decision.
Thank you, Stephen. The next question is for FC3. Is there any specific fuel that is considered more interesting? So is TRISO disposal of interest?
Well, that sounds similar to the earlier question, and our mission is to look at disposal of currently used fuel in primarily in commercial nuclear reactors, and that would include. So we're looking at low burnup and high burnup of conventional uranium oxide fuels. We are also, to some extent, at least in the disposal side, considering other DOE and DOD fuels, but we're not looking at experimental fuels. That's not within our mission. So that would be a no to TRISO. Yeah.
Okay, thank you, John. Is the development of alternative waste form for disposal of high-level nuclear waste appropriate to which topical area?
Let me add on this one.
Okay.
Okay, John, so if you want to prepare the waste form for alternative method, that will be in the material call. That's, I believe, tomorrow. So in the advanced material for fuel cycle applications for innovative waste forms. For disposal, I would like John to address that. John, go ahead.
I'm not positive what you're talking about, but again, we're talking about disposing conventional spent fuel and high-level radioactive waste from currently operating commercial nuclear reactors. At this point, we're looking at taking the fuel rods as they're discharged from the reactors. We're not looking at any transformation. And I thought I meant to sort of cover that anyway in the areas that are not relevant. But again, under SC5, if you have something in that area that you see that addresses our mission in FC3, you can propose it. But we're not looking at we're not currently looking at changing the waste form. No. That's it.
Okay, thank you. Thank you, John. To follow up on Stephen's comment about the advanced nuclear materials topic, that topic will be presented tomorrow, Thursday, August 11th at 3 p.m. Eastern.
Thank you.
For FC3 and FC4, is the degradation of high-level nuclear waste glass of interest?
Hi, this is John Orchard again. Yes, high-level waste glass form is typically, in my experience, a byproduct of the DOD waste, and that is something we're looking at. Let me think. It's part of the waste package, and it would be under the performance assessment or the GDSA. It's not a topic that we are currently investigating. It's not directly related to the mission, but I could see that it could be an SC5 other topic if it if it could show how that would cross-cut with our disposal mission. So I would put it in FC5. I don't see it as directly applying to FC3, and certainly not to FC4.
Thank you for that clarification, John. The last question here is for FC4. And the question is, would both experiments and modeling of chlorine-induced stress corrosion cracking be relevant to the NE mission?
Yes. Yes, that's something we're looking at. Yes.
If there's no
think-
more questions, may I just comment on something?
Please do.
People ask about tricycle disposition, also about irradiation during the disposal or storage. If you are interested in reprocessing of tricycle fuel using aqueous phase or molten salt phase, please feel free to submit to FC1 or 2, respectively. If this is using vapor phase to processing tricycle fuel, you can go to the FC5. And regarding irradiation, the same thing here. We welcome the irradiation studies effects on aqueous as well as molten salt system. Thank you.
Thank you, Stephen. And Stephen, as you were speaking, another question did come in. And so I'll ask this final question. Where would fundamental radiochemistry of radionuclides go under?
It would depend. Depends on what kind of application or purpose of studying that. If you just study the irradiation effect, then just like I said, 1 and 2 for during the reprocessing of it for the repository or for the disposition or for the storage transportation, then go to 3 and 4. If this is purely for scientific blue sky things, there's a nuclear chemistry area. I forgot which one is covered that one. Maybe tomorrow. So nuclear chemistry area. So you can go that route as well.
The scope Stephen's referring to is nuclear chemistry, which is a strategic needs area that was briefed yesterday.
Oh, it was yesterday. Okay.
Yep. It's I think the work scope code on that is SN3.
Yeah, sorry, I missed that one.
Okay, everyone. I think that is all the questions we have for this section. Thank you so much to our presenters.